now we move to consider a loop of current, or a current loop, and in a magnetic field, and in particular in a uniform magnetic field, where we will see and derive an expression for the torque that the magnetic field exerts on this loop. As we have just said, if we have a uniform magnetic field, then any closed loop of current will exert zero net force. But as just we are going to show here, this loop will feel a torque, and it will be rotated by the magnetic field. To this end, let's consider this figure. In this figure here, we have this rectangular loop. For simplicity, we are considering rectangular loop, but at the end, our result actually, we will declare that our result generalize, that we will derive at the end, will generalize for any, will be valid for any loop of any shape. Okay? So this is in the plane of the screen. So think of it as the plane of the screen, this rectangular loop, and it carries a uniform current, and the current is flowing counterclockwise. There is a uniform magnetic field in this space that is flowing towards the x direction. So it's in 3D in the whole space, and it's flowing parallel to the plane of the screen, and so parallel to the plane of the loop. This loop is in that magnetic field. Now, there is no magnetic force eventually and evidently on parts 1 and 3, on sides 1 and 3 of the rectangle, because of the simple fact that this is the current here is parallel to the magnetic field, here it is anti-parallel to the magnetic field, and you remember the result, the relation IL cross B. So if L and B are parallel to each other or anti-parallel to each other, then in this case the force, the cross product will be 0 in this case. So this side and this side 1 and 3 will not feel any current because of this fact. However, side 2 and 4 will feel a force because both of them are actually perpendicular to the magnetic field. So the L vector here is downwards, the L vector here is upwards, and both are perpendicular to the magnetic field. And the magnitude of these forces, because the angle between L and the magnetic field is pi over 2, is just the current multiplied by the length of each of them, which is A, as you can see from here, multiplied by the magnetic field. So this is the force, magnitude of the force on this side, and the magnitude of this force on this side, so on sides 2 and 4. Now, what about the direction? Well, you just apply the right-hand rule. L is downwards, B is this side, so it is on F2 in this case is out of the page, and F4 is into the page. It's F4 into the page. So for example, for F4, this is I, the magnetic field is to the right here, so F close towards B, and it is into the page. The opposite applies to 2. So here we have a force into the page, here we have a force out of the page. Okay? Now, so these forces are equal and opposite because they have the same magnitude, but they are in opposite directions. But of course, in this case, the net force on this loop in this case, in the absence of forces in the upper and lower sides, is 0. But since these two forces act on different points of the object, then the net torque in this case will not be 0. And this loop will rotate evidently under the action of the forces exerted by the magnetic field. And this is what we are going to investigate. So this is the first thing that we conclude. Really, when you have a loop, this rectangular loop, when you put it in a uniform magnetic field, there will be a force exerted on this loop, and so it can rotate. To analyze this, let's take a different view. Now, this view here is we are looking at it from this side. What I mean by this is the following. The rectangle loop was this. So this is side A, these are the sides A, and these are sides B. And this was in the plane of the page, or of the screen. Now, if you just put it horizontally this way and look at it from here, then this is what you see. So this is the edge. This was the lower edge of the rectangle when you look at it here. And so the magnetic field in this case will be, as you can see here, it is parallel to the plane of the sheet. So it is just put the sheet down this way and look at it from here. Now the current in here, this is what was wire 4, so it is side 4, it is this was side 2. So side 4, the current was threading into the page, and here it was coming out of the page. So when you look at it, this is how it looks, okay? Now the whole side, this is easier to analyze in this case and to visualize. So in this case, this side will have force. In this case, it was out of the page, so when you put it this way, it is up. The side 4 had a force into the page, so when you put it in this way, it is downwards. So this feels a force downwards, this feels a force upwards, and so the torque now will make this rotate in this direction, okay? Now, so we'll have a net torque about a point O at the center of the rectangular loop. Now let's find the expression for this torque. This is the maximum torque for a reason that will become apparent shortly. How you find it? Well, what is the torque of this force? Well, at the magnitude, it is F multiplied by the distance to the point O multiplied by sine the angle between this distance and this. But the sine here is pi over 2, so it's just F2 minus this distance. But the width of the rectangular loop was B, so this distance is just B over 2, and this is B over 2. So the torque of this force is F times 2 times B over 2. The torque of this force is F4 times B over 2. And since they are both equal, I mean they are just IAB, so when you add them up together, you add them because they are producing rotation in the same direction. They have the same sense of rotation. So when you add them up together, you get this expression. I multiplies by AB multiplied by the magnetic field. Now, AB for the rectangle is this length multiplied by this length, but this is just the area, okay? And therefore, you can write tau maximum, the maximum torque is I multiplied by the area multiplied by the magnetic field. So this is the maximum torque that a rectangular loop, actually any loop can, not only a rectangle, it can be shown that this applies to any loop felt, the torque felt by this any loop of area A when it's placed in a magnetic field. The maximum torque occurs only when the magnetic field is parallel to the plane of the loop, like what we had here. Look, when it was in this way, the magnetic field was here, so it was parallel to the plane of the loop. Now here, when I put it this way, the magnetic field was still now parallel to the plane of that loop, okay? So in this case, we have the maximum, as we will just see. What happens if it was not parallel? Well, it's like in this case, this is the situation, okay? So the loop is not, this is the magnetic field still here, but the loop is tilted now, okay? So in this case, the torque will be less than the maximum torque that we have just calculated. How is that? If you look here, when it is tilted, the forces on 2 and 4 on these two sides will still be the same, I mean, because the current direction doesn't change. So here it will be still up, here it will be still down. But now the torque of this force about O will not just be F2 multiplied by B, but it will be F2 multiplied by B sine theta, because you know this is called the force arm, or the lever arm of this force. It is the distance from the force line of action, the force, to the point about which you are calculating the torque. So it is B over 2 sine theta, and the same applies for this. It is B over 2 sine theta, and therefore the torque will be IAB sine theta. Why is this? Because A here is just AB, but we know we had B over 2 sine theta and B over 2 sine theta, so we will get small b. I'm talking about small b sine theta, and so the whole thing will reduce to I tau is equal I times A times B times sine theta. So this is the torque. Well, now this, if you exclude I, this looks like some sort of vector product. You know, you have two quantities, two magnitudes, and then you're multiplying by the sine the angle between them. This on one hand. On the other hand, we know from our previous study of mechanics that the torque is a vector. If you remember, the torque tau was equal of a force about a given point O was R, the vector that goes from the point where you want to calculate the torque to the point of action of the force, that was the R vector, cross F. And it was a it was a vector also, okay? And probably this is where you first encountered a vector product in your study. And therefore, actually I can utilize this and I can define the torque now as a vector and as the vector product now of two vectors now. Okay, so I write this torque as the vector product of two vectors now. What are these vectors? Well, B is a vector, of course, because the magnetic field is a vector. But what is the other vector? Well, the other vector is the area vector. Okay, so this is a vector A, as you can see. This is the vector. So this is my area. This is a vector normal to that area. And this is the area vector. Well, we have seen this before when we talked about magnetic moment. I will just remind you about this. So the vector A is a vector normal to the area. And so I can write tau now, the torque, as I, which is the scalar quantity, A cross B, the area vector crossed into the magnetic field vector that's acting here, and the magnetic field is uniform. Now, so from here, it is evident that the torque here has the maximum value when the field is perpendicular to the normal of the loop. In other words, from here, when the angle between A and B is pi over 2, that's B is perpendicular to A. If B is perpendicular to A means the field lines are parallel to the plane. So now we do not talk about the plane, we talk about the normal. So we say when B is normal to the area vector, then in this case we have maximum torque, because sine theta will be equal to 1. Theta will be pi over 2. Now, if the torque vector will be 0 when the field is parallel to the normal. In other words, if this is the plane, if it was inclined this way, this is the area vector, or it may be here. The field line is coming in this direction, so the angle between the area vector and the field is either 0 or pi over 2. And in this case, this cross product, this value, and so the cross product will be 0. So it will not feel a torque. So if you have a magnetic field flowing from towards the x direction uniform, and you put a loop in this direction so that the area vector is parallel or anti-parallel to the magnetic field, this loop will not feel neither a net force nor a net torque. It will not rotate in this case. Okay? So that's what we give it. Now, the question is, I said, okay, A is, we define it as the area vector, but let's look a bit closer at this A. Now, if this is the area of the loop, and they say it's perpendicular to the plane of the loop, but you have two normals. You have this normal, and you have a normal here, down. Okay? So this is a normal, this is a normal. Which normal of these you are going to use? Okay? Here comes right-hand rule, and it says that you let your right-hand fingers curl with the direction. This applies to any loop, by the way, not only for our rectangular loop. You let your right-hand fingers curl with the direction of the flow of the current. In this case, your thumb gives you the direction of the area vector that you have to define. Okay, so this is how you define it. So it's not arbitrary. It is actually governed by the direction of the current. So this is how you define this area vector. It's normal, given by the right-hand rule, and its magnitude, it's the area vector. What's magnitude equal? Its magnitude is equal to the area. So it's a vector which has normal to the area, but its modulus is equal to the area of that loop. Okay? Now, of course, this is reminiscent of something that we have introduced before when we talked about the magnetic moment. You remember we defined the magnetic moment, or the magnetic dipole moment more precisely, of any loop, and saying that it is equal to the current passing through that loop multiplied by this area vector that we have just introduced. And so, this relation, IA vector, this quantity, is just mu, the mu vector, the magnetic dipole moment. So I can write tau now, the torque on the current carrying loop, as the vector product of two vectors. One of them is mu, which is the magnetic moment of the magnetic dipole moment of the loop, and the second is the magnetic field. This is a very simple and elegant expression. So it says that, and this is general and applies to any loop, not only to the rectangular loop. We have derived it for the rectangular loop for simplicity, but this can be derived generally for any loop, planar loop. So it says that if you have any loop, current carrying loop, okay, and you put it in a uniform magnetic field, then this will exert a torque, generally speaking. And this torque, to find this torque, you have to know one thing, two vectors only. The first vector is the magnetic dipole moment vector, which is defined, which is mu vector, which is defined by just the area multiplied, vector multiplied by the current. And the other is the magnetic field that is penetrating this loop. If you find them, you can find what is the torque at any instant. Okay? This is a very simple and elegant expression. And this applies not only for rectangle, circle, any shape, even any irregular shape. So it is a very nice and elegant expression. So this is where we can utilize this magnetic moment. So we think now, we call actually any loop, we call it a magnetic dipole moment. Okay? Because, and when you put it in a magnetic field, this will rotate. It will exert a torque, the magnetic field will exert a torque and it will rotate. Actually, it will dance. Now we have seen this similar expression before when we talked about the electric dipole. When we had an electric dipole and we used to put it in an electric field, and we saw that it experiences a torque, and this torque is given by P cross E in this case. So you can see the similarity. So it's just B goes to E, mu goes to P. As simple as that. Okay? Again, I emphasize that this relation is valid for loop, for any loop of any shape. Now we can go even further. If you recall, when we introduced electric dipole, electric field, we said that there is an electric potential energy actually accompanying that. As it rotates, okay, we have transfer of potential energy into kinetic energy and vice versa. Okay, so we have defined in that case a potential energy of the magnetic dipole in electric field, and it was just minus mu dot P, the dipole moment of the electric dipole moment of the dipole. Now here we exactly follow the same lines, and we define magnetic the dipole, the potential energy of a magnetic dipole of magnetic moment mu vector in a magnetic field B. And again, the definition is quite similar, minus mu dot B. In the case of the electric field, it was minus P dot E. So it's very similar, okay? So this is the potential energy of a dipole in a magnetic field. And as you can see, when the dipole is parallel to the magnetic field, when the dipole is parallel, the dipole moment is parallel to the magnetic field, that is, if the magnetic field, for example, is along the positive x direction, and the dipole moment is in this direction, and the area vector is in this direction, so that there is no torque in this case, then this is the state of smallest potential energy. This is the stable equilibrium position. It is maximum when it is opposite. As you can see, when the angle between them, because mu dot B is what? Mu B cosine theta. Okay? So it is maximum when theta is equal pi, which means B is opposite to mu, and in this case it will be plus mu B. It is the energy have ranges between these two, and it is zero when the magnetic dipole and the magnetic field, the magnetic dipole moment and the magnetic field are perpendicular to each other. In other words, if this is the electric field, again, is towards the positive x-axis, in this case, if the electric field, the magnetic field, and if the magnetic field is in this direction, then the magnetic dipole is perpendicular in this case. If it's in this way, so perpendicular to the field, then in this case the angle is pi over 2, and this, in this case, the energy, potential energy is 0. But it's not the lowest potential energy, because the lowest potential energy is minus mu B. It is here. Now we have two checkpoints, quite interesting checkpoints. Please try to do them, as they will enhance your understanding of the topic. We will do some numeric example about calculating the torque on dipoles in uniform electric fields elsewhere.